Welcome to this tutorial on using ROS2 with MATLAB and Simulink. Here's the learning path we'll be following throughout this tutorial. In this session, we will focus on ROS2 time and synchronization between nodes, which are crucial for ensuring coordinated operation in distributed robotic systems. Let's take a closer look at the outline for today's session. We'll begin with an overview of the ROS2 time concepts, explain the different types of time in ROS2. Next, we'll demonstrate how to access the current ROS2 time in both MATLAB and Simulink. Finally, we'll show how to synchronize nodes in both MATLAB and Simulink. Does the algorithms or systems running as a ROS2 node rely on timestamps to ensure both real-world and simulation environments seamlessly? Do we need to ensure consistent timestamps across nodes, which is critical for different robotics tasks, such as sensor data fusion, perception, and control? When logging and playing back the ROS2 data and bag file, does it require timestamps? All these use cases, and many others as well, rely on ROS2 time for consistent, precise, and synchronized time management across real-world, simulated, and hybrid robotic systems. ROS time refers to the time abstraction used in ROS. There are two key concepts in ROS time: system time and the simulation time. The system time refers to the current time on the computer's system clock. It's also known as the wall clock, or wall time, like the clock on the wall of your lab. In contrast, simulation time is used when running simulations or playing backlogged data. It allows you to accelerate, slow down, or step through the system's perceived time. Simulation time is broadcast on the /clock topic. To enable a ROS node to use simulation time from the /clock topic, the useSimTime ROS2 parameter for the node must be set to true. If useSimTime is set to false, the node will use the machine's system time. The /clock topic in ROS2 publishes messages of the type built-in interfaces /MSG/time. These messages contain the current time information in seconds and nanoseconds. Next, we will demonstrate ROS2 times in MATLAB. In this example, we will demonstrate how to access ROS2 time using MATLAB. First, start by creating a ROS2 node. Create a ROS2 parameter object associated with the ROS2 node. Listing all available parameters, we will find the useSimTime parameter. Retrieve the useSimTime parameter. By default, its value is 0, false, meaning that the ROS2 time refers to the system time. Now we are ready to access the ROS2 time, where returns the message type and the current time in seconds and nanoseconds. We can investigate the structure and details of the ROS2 time message. Finally, we can convert the ROS2 time to the MATLAB datetime format for easier interpretation and analysis. If the useSimTime parameter is set to 1, true, ROS2 uses simulation time, which depends on the /clock topic being published. In this example, we will create a ROS2 node in Simulink to publish the /clock topic. In the Simulink model, add a digital clock block. This block outputs the simulation time at the specified sampling interval. We also add a message block and a publisher block to create and publish ROS2 messages. The Simulink model includes blocks to convert the simulation time into the ROS2 time format in seconds and nanoseconds. We then start running the Simulink model, and it will generate and publish the /clock topic. In MATLAB, list the available topics, and the /clock topic should appear in the list. When retrieving the ROS2 time from the /clock topic, we will see that it reflects the simulation time from Simulink. Next, we will demonstrate ROS2 times in Simulink. In this example, we will demonstrate how to access ROS2 time in a Simulink model. In the Simulink model, add a ROS2 current time block. This block outputs the current ROS2 time, which depends on the use sim time parameter. Run the Simulink model. By default, the use sim time parameter is false, 0. As a result, the block outputs the system time, which corresponds to the computer's system clock. We will then interact with the Simulink ROS2 node using MATLAB. Open a MATLAB script. First, list and select the Simulink ROS2 node. Create a ROS2 parameter object associated with the Simulink node and list all available parameter. The use sim time parameter should appear in the list. Retrieve the use sim time parameter value, which it's 0, false. Set the parameter to be true so that the Simulink ROS2 node uses simulation time. This change requires the /clock topic to be published. Open another Simulink model to publish the /clock topic. Once the clock topic is being published, the ROS2 time retrieved by the ROS2 current time block should reflect the simulation time from Simulink. Next, we will demonstrate ROS2 node synchronization in MATLAB. In ROS2, synchronization between nodes refers to coordinating the activities or data streams of multiple nodes to ensure consistency, correct sequencing, and proper timing. For example, combining data from multiple sensors, such as camera and LiDAR, requires timestamps to align data for processing. For controllers, we need to ensure that a control command node gets the most recent sensor data. For sensor fusion or SLAM, simultaneous localization and mapping, simultaneously using IMU, odometry, and LiDAR for mapping and localization needs synchronized timestamps. For multi-robot systems, synchronizing data between robots ensures consistent shared state understanding. In MATLAB, using the ROS2 rate object allows you to execute a loop at a fixed frequency. It uses the ROS2 node as a source for time information depending on use SimTime ROS2 parameter. If use SimTime is set to false, the ROS2 time is based on the system clock of your computer, called system time or wall time. If use SimTime is set to true, the ROS2 time is based on the simulation time, which requires the published /clock topic. In this example, we will demonstrate how ROS2 rate enables ROS2 nodes to run at fixed frequencies in MATLAB. First, we begin by creating two ROS2 nodes, each in a separate MATLAB instance. By default, the use SimTime ROS2 parameter for each node is set to 0, false, indicating that ROS2 time is based on system time. Create a ROS2 rate object with a desired rate of 1 Hz. We then start a loop to print the current time and the total elapsed time for the entire loop. Each step on these two ROS2 nodes takes 1 second, resulting in a total time of 20 seconds for each node, as expected. Next, we set the useAtSim time to true, making the ROS2 time based on simulation time from the /clock topic. If we attempt to start the loop now, we encounter an error indicating that there is no /clock topic available on the ROS2 network. To resolve this, we open the previous Simulink model to publish the /clock topic. Note that the simulation pacing is 1, meaning the simulation time matches the system time, in real time. Run the Simulink model and return to the two ROS2 nodes in MATLAB to start the loops. As expected, these two nodes step every second with a total elapsed time of 20 seconds, similar to the previous step. Going back to the Simulink model, if we set the simulation pacing to 2, the simulation time is twice as fast as the system time. Let's see how the ROS2 nodes in MATLAB will behave. We can see these two nodes step faster, with a total elapsed time of 10 seconds. Conversely, in the Simulink model, set the simulation pacing to 0.5, which makes the simulation time twice as slow as the system time. Let's see how the ROS2 nodes in MATLAB will behave. Here, these two nodes are steps slower, resulting in a total elapsed time of 40 seconds. In the previous session, we explored how nodes were synchronized using ROS2 rate, a method that is considered loosely coupled. This approach allows each ROS2 node to operate independently based on its own internal timing mechanisms. While this method is effective for many applications, it may not be suitable for scenarios that demand precise timing coordination between nodes. In situations where strict timestamps or precise sequencing are crucial, relying solely on our ROS2 rate might not suffice. For example, applications involving sensor fusion or coordinated control of multiple robotic components often require nodes to operate with a high degree of synchronization. In these cases, discrepancies in timing can lead to errors or inefficiencies. To achieve tighter synchronization, it is beneficial to utilize the timestamps embedded within ROS2 messages. These timestamps provide a consistent reference point across different nodes, ensuring that all components are operating based on the same temporal framework. By accessing and utilizing these timestamps, we can implement more robust synchronization mechanisms, allowing for precise coordination and sequencing of events. In practice, this might involve designing nodes to subscribe to specific topics where messages include timestamps, such as the header message type, and then using these timestamps to align operations across nodes. This approach can help ensure that all nodes process data in a coherent and timely manner, which is critical for maintaining the integrity and performance of systems that rely on precise timing. In this example, we will demonstrate how to publish and subscribe the header message in MATLAB. First, we begin by creating two ROS2 nodes, each running in a separate MATLAB instance. Create a publish for messages of type header. This message type includes a stamp field that contains ROS2 time information, represented in seconds and nanoseconds. We initiate a loop where the current ROS2 time is assigned to the stamp field in the header message. This message is then published every second. On the subscriber side, we subscribe to the header topic. A callback function is used to display the received timestamp. This example illustrates the basics of publishing and subscribing to header messages in MATLAB, allowing for the exchange of time-stamped data between nodes. Next, we will demonstrate ROS2 node synchronization in Simulink. In this example, we'll use the TurtleSim Simulink model to demonstrate the synchronization of ROS2 nodes. First, open the Simulink model, which includes a path-following controller designed to guide the turtle along a predefined path. This model publishes commands to the TurtleSim simulator running in an Ubuntu virtual machine and subscribes to feedback on the turtle's state. Note that the simulation pacing is initially set to 1, indicating that the Simulink model operates in real time. When we start the Simulink model, we'll observe that the turtle follows the path as expected. Now, if we adjust the simulation pacing to 10, meaning the Simulink model runs 10 times faster than real time, let's see how the turtle behaves. Upon starting the Simulink model again, we'll notice that the turtle no longer follows the desired path. This example demonstrates how to timestamp a ROS2 message using the computer's current system time. First, open the Simulink model. Use the current time block and a bus assignment block to assign the current ROS2 time to the stamp field of a header message. Then publish this message on the desired topic. Start the Simulink model to publish the header message. In MATLAB, create a subscriber to listen for the header message. We will see how the MATLAB node displays the received timestamp in each frame. I hope you now have a clear understanding of ROS2 time and node synchronization in both MATLAB and Simulink. Thank you for participating in this session. In the next session, we will explore how to deploy ROS2 nodes in MATLAB and Simulink as standalone nodes on target systems. By the end of this session, you will have comprehensive understanding of generating C++ code from ROS2 nodes and deploying it to local or remote device targets. I look forward to continuing our journey in the next session.